Can artificial intelligence support sustainability without creating a larger environmental burden of its own? This script explores how sustainable AI solutions are developed, from core principles and practical steps to real examples, challenges, and industry applications. You will also see why energy efficiency, data efficiency, fairness, and trust all matter in this work. Developing sustainable AI solutions means designing, implementing, and managing AI technologies so they maximize positive impact on sustainability while minimizing environmental footprint. The overall approach in this material combines development principles, practical steps, examples, challenges, and application design. Together, these elements show how AI can be built more responsibly and more effectively. Sustainable AI should minimize energy consumption by using efficient models and hardware. It should also be scalable and flexible through modular systems that fit existing infrastructure. And it must promote ethical and responsible AI through transparency, reduced bias, privacy, and security. The development process starts by identifying sustainability objectives, such as reducing waste, conserving energy, or improving resource efficiency. Next comes selecting high-quality data and suitable models. Then applying green AI practices during training and deployment. Stakeholder engagement and continuous monitoring complete the cycle so the system can be refined over time. Some of the clearest examples come from renewable energy and smart agriculture. Predictive analytics can forecast energy production and demand for wind and solar systems. One example says Google AI predicts wind patterns, increasing wind farm energy efficiency by 20%. In agriculture, AI-powered sensors and drones support precision farming while reducing water and fertilizer use. Sustainable AI also appears in waste management and climate action. Robotics and computer vision can sort recyclable materials and reduce landfill waste, with AMP Robotics named as an example of automated sorting in recycling facilities. For climate action, AI can monitor conditions in real time, predict extreme weather events, and support disaster preparedness. The material highlights 4 major challenges. Training complex AI models can consume significant energy and contribute to carbon emissions. Limited access to high-quality and inclusive datasets can weaken effectiveness. High initial costs and limited infrastructure can slow adoption, especially in developing regions. Ethical issues such as bias, fairness, and data privacy also require attention. Model pruning removes redundant parameters, so models become smaller without compromising accuracy. This lowers computation and energy use. The material gives large language models like GPT as an example, where pruning unnecessary weights can lead to faster inference and lower energy use. 2 more techniques focus on making models lighter. Quantization converts weights and activations from high precision to lower precision, reducing memory and computation needs, with TensorFlow Lite given as an example. Knowledge distillation transfers knowledge from a larger teacher model to a smaller student model. MobileBERT is presented as an energy-efficient example for natural language processing. Efficiency also depends on hardware and deployment choices. Specialized processors such as tensor processing units and edge AI chips are used to reduce energy consumption during training and inference. The NVIDIA Jetson series is named as a low-power solution. Distributed training with tools like Horovod can reduce time and energy, while edge computing and AutoML can further lower resource use. Google DeepMind used reinforcement learning to optimize data center cooling, reducing energy consumption by 40%. The case studies show what these ideas look like in industry. Tesla Autopilot uses optimized neural networks on custom AI chips for real-time processing with lower power consumption. Amazon Alexa and Google Cloud AutoML are also given as practical examples. 02, 03, 04, 05. The key idea is that AI systems can still achieve strong performance with smaller datasets. Data efficiency is presented as essential for reducing the resources, time, and cost needed for model development and deployment. That makes them more accessible and more scalable across different industries. Several approaches support data efficiency. Data augmentation expands training sets by creating modified versions of existing data, such as flipping, cropping, rotating images, or adding noise to textual data. Transfer learning adapts pre-trained models to new tasks with limited data. Synthetic data generation simulates real-world data sets and can reduce privacy concerns in sensitive scenarios. Google AutoML used transfer learning to help small businesses create AI models without vast amounts of data. OpenAI GPT models are described as adapting pre-trained language models to specific tasks with small labeled datasets. Waymo uses synthetic data for rare driving scenarios, and NVIDIA used generative adversarial networks to create realistic human faces. Bias in AI can create unfair outcomes, reinforce inequalities, and damage trust. The material identifies three main forms. Data bias comes from imbalanced or unrepresentative datasets. Algorithmic bias comes from flawed assumptions or design choices, such as prioritizing accuracy over fairness. Societal bias reflects existing inequalities already embedded in data or system design. Bias detection toolsets can be detected with tools such as AI Fairness 360 by IBM, Google Fairness Indicators, and explainable AI techniques that reveal decision patterns. LO2. Mitigation methods include resampling, reweighting, fairness constraints, and adversarial debiasing. LO3. The examples include SMOTE for minority samples and constraints based on demographic parity or equal opportunity. LO405. Trustworthy AI is described as essential for sustainable development because it supports ethical, reliable, and accountable deployment. The main principles are transparency, explainability, and accountability. Transparency means operations are clear and understandable. Explainability helps stakeholders understand decisions. Accountability assigns responsibility for outcomes, so systems align with ethical standards and societal expectations. Ethical AI frameworks prioritize fairness, safety, privacy, and inclusivity. With the European Union Ethics Guidelines and ISO IEC 22989 named as examples. The material also points to ethical frameworks and practical implementation. In practice, IBM Watson Health is described as using transparent and explainable models, while Rainforest Connection uses open methodologies to detect illegal logging. For agriculture, the focus is precision farming and sustainable practices. AI systems can analyze soil health, weather patterns, and crop conditions to optimize resource use. This can reduce water, pesticide, and fertilizer use. Blue River technology is cited as selectively applying herbicides and reducing chemical usage by 90%. Predictive analytics can also support food supply chain management and reduce food waste. In the energy sector, AI is used for forecasting and renewable energy management. It can predict demand and supply fluctuations to improve grid operations. Google is named as an example of AI-powered energy management that optimizes wind energy output. AI models can also balance renewable sources with traditional power grids, improving reliability and reducing dependence on fossil fuels. Project development begins by defining sustainability objectives for a specific sector, then collecting high-quality representative data. Model development should use energy-efficient methods such as transfer learning and model pruning, followed by scalable deployment that may include edge devices. Impact is evaluated through environmental, economic, and social metrics such as reduced resource use, lower costs, and improved community outcomes. Sustainable AI is not just about what artificial intelligence can do, but how it is designed, trained, deployed, and governed. You have seen the principles, steps, examples, challenges, and industry applications that shape this approach. You have also seen why energy efficiency, data efficiency, fairness, and trustworthy practice are central to sustainable AI solutions.